Welcome again. I'm Neil. Today's chapter is all about circuitry, but more specifically, the components, the basic components that goes into an average circuit. Now, the picture behind me here is a typical circuit board. There's all kinds of things going on in here. It gets quite complicated. So at this particular level of physics, we're not so much interested in the intrinsic details of the million different things that you see here. But it really all goes back to the Italian, Alessandro Volta. In 1799, he invented essentially what was the world's first battery. So batteries gave us a way to store charge and to release that charged energy and to do useful work with it. So many different devices have come along since the time of Volta. So today we'll just touch on just a few of the basic things as this particular chapter does. We'll talk about batteries, capacitors, and resistors. Now, again, there are many other things, but it makes the circuitry quite complicated, and that's a bit above the scope of what we're trying to do here. So, in this particular chapter, we're going to talk about batteries, how they're put together. A battery, it's essentially a battery. There's thousands of different kinds of batteries. Essentially stores charge. There's an electrode, two electrodes actually, positive and a negative, embedded in some kind of gel or liquid and called electrolyte. A chemical reaction is where it all starts. A chemical reaction, it separates the charges. The chemical reaction occurs between the electrolyte and the electrodes. And the chemical reaction separates the electrons and leaves behind positive ions, cations behind. And so the segregation of charge builds up a potential difference. An electric field ensues inside of the battery. And when the terminals of the battery are connected via some conducting medium, like a piece of copper wire, for example, in a closed loop, a closed circuit, the built-up potential difference tries to discharge itself. That is, the electric field that's built up between the electrodes and the battery, due to the chemical reaction, exerts a force, a Coulomb force, really, on the free charges within the wire, the conducting medium. And the charges are allowed to move, and this generates an electric current. Of course, if that's all there was to it, we wouldn't have much use for the battery, because eventually, in a very short space of time, the battery would be discharged by actually short-circuiting the battery. It discharged very, very rapidly if we didn't put a load onto the circuit. Now, these loads take on different forms: resistors and capacitors, inductors, and a host of other devices. So as we go along with this chapter, we'll talk about the difference between ideal EMF and true EMF. There's a difference that has to do with internal resistance within the battery. It needs to be overcome and some energy is lost. So the ideal EMF, electromotive forces, is not the same as what you actually get, or the useful work that you can get out of the battery, the true EMF. Batteries can provide both a direct signal, DC current, and an alternating signal, an AC current. There are pros and cons to each. Typically in very small devices like toys and games and stuff, the DC batteries, they work fine. They tend to discharge somewhat readily, but they're portable. AC batteries, they're good for much larger things. The signal fluctuates over time. We can actually convert an AC source into a DC signal by using something called a converter. So those kinds of details are dealt with in the chapter. So some of the basic designs for things like capacitors. A capacitor actually is used to store energy in the form of an electric field. There are different kinds of capacitors. Some of them are shown here. Typically represented by two plates opposing each other, connected to different ends of the battery, one to a negative end, one to a positive terminal of the battery. So each plate, depending on which terminal of the battery is connected to, takes on that charge. An electric field builds up. So As a matter of fact, capacitors are very, very common. Every time you tune into a radio station or change a radio station in your car, for example, that dial that you're turning, what that does, it changes the distance between these two plates over here. And that alters the frequency of the current within the circuit to match whatever signal a particular radio station is using to broadcast a signal. So when you match up with that broadcast signal, you've tuned in to a radio station. So capacitors are extremely common. In every circuit you'll find many different kinds of capacitors. Now, certainly there can be more than one capacitor in a circuit, so depending on how these capacitors are used, they can be aligned in series or in parallel. And the equivalent capacitance of the circuit, the energy storing ability, that is, depends on the arrangement, how the capacitors are lined up, opposing each other or one after the other in series. So the details of that are dealt with in the chapter, and several examples are done, calculations of the equivalent capacitance. We also talk about in some detail, after we get past all of these examples with capacitors. The reader can see there's quite a few examples to learn from. We can talk about the difference between resistance and resistivity. In a nutshell, resistivity is a property of the chemical composition of a material. It depends on such things as the imperfections in the material, the crystalline structure, any kind of contaminants are in the material. So it's more of a dependent on the chemical nature, resistivity is. Whereas resistance, it's more of a macroscopic property. It depends on really the structure, the arrangement of the material with a specific resistivity. So if we were to take a piece of wire of a fixed diameter and length, it has a certain resistivity. If the wire is made of copper, for example, it's got a fixed resistivity, and that you can't change. However, depending on the configuration you bend and you fold this piece of wire into to use it into a circuit board, it will change the overall resistance to flow of electric current. So that's what I mean about the macroscopic properties can change. So resistance and resistivity are not the same thing, but one is a function of the other. It turns out that resistance actually is a function of resistivity, as we shall deal with in quite some detail in this chapter. And so the reader is going to have a great handle on the differences of the two. The nature of resistivity is actually shown how it's calculated. It's the ratio of the electric field to what's called the current density. All of these things will make much more sense to the reader as they go through the chapter. Conductance power in a circuit, it's also derived as we go along. On one of my treks, I was on my way on a Dutch expedition vessel to Antarctica, the bottom of the world, and I was able to look at the circuitry on board on the ship at the captain's deck. It was quite fascinating. A lot of old school technology, but that's kind of what you need: rugged old school circuitry and technology to get you to one of the roughest places in the world. Finally made it down to the bottom of the planet here. But when I finally made it to Antarctica, there are a lot of research stations there. One of the research stations I visited belonged to Argentina. Virtually every country has a research station there, every developed country, that is. So this is one of those. And I devised a problem to just, getting to the research station is no easy task. It's a death-defying ascent. And finally made it. It's all frozen over in icicles. But these research stations are far and few in between. Not much to do in Antarctica when your ride leaves you behind. These research stations are far and few in between. So I derived an example for the reader. If we are to use a cable to link two stations that are a certain distance apart, what kind of properties, specific properties and dimensions we need to have. So it's great if you're an electrical engineering major. This chapter is very important to the reader, you know, if that's going to be your career. So we derive the problem to calculate certain properties of the wire that needs to be used when they link these research stations together that are very, very far away. Another interesting example, so this is all the way back stateside, the redwood forest in California. These are some of the oldest trees on Earth. This one in particular is called General Sherman. This is the single largest living thing on our planet. It's several 100 feet high, and it's believed to be about 3,000 years old. So these giant redwood trees, they're so large that this one is pretty interesting. This one is called a Chandelier Tree. They've actually cut a tunnel right through it, and a car can drive right through it. Maybe some readers who've been to the redwood forest have driven through this before. So that's my car in there, driving through there. Now there's a significant amount of rainfall because of the location of the redwood forest. That's why the trees grow so large. There's no shortage of moisture in the atmosphere. That's because of its proximity to the Pacific Ocean. It's very close by, and all of the winds coming off the Pacific Ocean moving eastward brings a lot of moisture to these forests, so the trees can grow very, very large, which means that the trees are perpetually coated with a thin layer of water. Now, water by itself, pure water, is one of the world's best insulators. It's not conducting at all. It's the contaminants in water that make it conducting. So certainly water that condenses onto the trees, that's conducting water. There's all kinds of contaminants mixed in there. So forest fires are very common. That's because lightning strikes in these regions can easily be transferred via the thin layers of water along the trunk, the very long trunk of the tree, down to the earth. And forest fires, which are not always a bad thing if they're naturally occurring, they need to clean out the forest floor to make room for new growth of the next generation of trees. Otherwise, things will get stuck in a rut. So natural forest fires are actually quite necessary, and this is one of the ways in which they can start. So I came up with a problem to calculate what the current is from a typical lightning strike that will be channeled down to the ground through the length of this tree, the Chandelier Tree, and by a very, very thin layer of water that would wrap itself around after a rainfall. So it's a very interesting example, actually. I think the reader will find that very, very cool, how that works. And the current that's transmitted through the trunk of the tree, it's just an unbelievable amount of current, by far greater than anything that's necessary to be fatal to animals and people, etc. And as with every chapter, there are several additional word problems to give the reader some more practice at the end of the chapter here. So I think the reader's going to have a great insight into basic electrical components, how they're put together, resistors, capacitors, and batteries in circuitry. Again, this is a really important chapter if you're a budding electrical engineer. Once again, I thank you for your time.